In this video, we're going to look at inferences for two population means. So, what exactly do we mean by that? So far, we've looked at comparing a population mean to some set value that we believe to be true. But here, we're going to look at two different populations. So, for example, suppose I had the faculty in a private institution compared to the faculty in a public institution. And we looked at all the faculty in all private institutions across the country and all the faculty in all public institutions across the country. So when we look at this, we consider these independent samples because the faculty are not one-to-one related to each other in any way. But we would take a sample from the first population and a sample from the second population. These samples do not need to be the same size. And we might go ahead and compute the mean of, say, their salaries for each of the samples. And then we would have to make a decision after comparing the mean of the salaries of the faculty in the privates compared to the mean of the salaries of the faculty in the publics. So what does this mean exactly? When we are doing a two population, we start with the assumption that the means we are comparing are equal to each other. Hence, our null hypothesis is always going to be mu1 equals mu2. Now, when we do this, we must define what population is mu1 and what population is mu2. This was done for us. Population 1, so mu1, comes from faculty in private institutions. Then, we make some sort of alternative hypothesis, which will be given to you, of course, based on some assumptions we make, possibly based on our sample. Perhaps we have this assumption that private institutions pay more than public. If that was the case, we would want to check to see if mu1 was actually greater than mu2. Maybe some people believe they pay less. We would go the other direction. Maybe we are checking to see if they're just not equal to each other. So that alternative could be one of three factors, just like when we dealt with one population mean. Could be less than, could be greater than, could be not equal to. But the key here, your null hypothesis is always going to be mu1 equals mu2, and also make sure you define those two populations. Now, there are multiple types of two population tests that we could go through. First of all, we have to determine if we have independent or dependent samples. The sample we just talked about was clearly independent. To understand what an independent sample is, it's easier to understand first what a dependent sample is. Think of a drug trial. If we're trying to lower the cholesterol in a group of individuals, we would check their cholesterol before a certain drug was given to them. We would check their cholesterol after a certain drug. Would it make sense in that case to take the average of group 1 compared to the average of group 2? Probably not. We want to look at the individual differences. Person 1, what was your cholesterol before and then after, and subtract before we take the means. That's what a dependent sample is. In an independent sample, we're just looking at the mean of the entire sample. In dependent ones, we have to look at the differences first because it matters, the before and the after. With independent samples, there's two different types we're going to look at in this. First one we're going to look at is a pooled t-test. This is normal, we're going to assume normality, of course, and these are normal distributions that have the same shape. So distributions that have the same shape mean they have equal population standard deviations. This assumption will be given to you if it's meant to be true for a particular problem. If it's given to you, then we would do what we call a pooled test because we're going to pool those two standard deviations together. We're going to weight them according to the sample size and pull them together, and we're going to introduce a new variable we're going to call S sub p to represent that pooled standard deviation. Now, what if they're not the same shape? What if we cannot assume equal population standard deviations? Then we do what's called a non-pooled test. And you will see when we go through it, in the non-pooled test, we do not find S sub p. We actually use the two individual sample standard deviations within our problem. The difference, one of the main differences between the two is calculating our degrees of freedom. And the first one, it's fairly similar. When you can pull them together, you add up the sample sizes and subtract 2, no longer subtracting 1 because we have 2 samples. But it becomes much more complicated to get an accurate degrees of freedom in a non-pooled test, which you will see. There is a third test, and it is discussed in our book, but we are not going to go through it in this course. But often students ask, what happens if it's not normal? What if our distribution isn't normal to begin with? We have tests for that. Again, we just don't discuss them in this course. There's something called a Mann-Whitney test that is discussed in one of the sections that we'll be skipping. I believe it's 9.4. And that's what happens if you have the same shape, but they're not normal. And then, of course, we have our dependent samples with the paired. So we are going to go over 3 different tests. In this video, we will go through a sample of test 1 and test 2. And then in the next video, we'll go through the dependent samples. So let's start our inferences for 2 population means using independent samples, assuming the standard deviations are equal. Again, how do you know you're using this test? You will be told this in the problem you're working on. I want to take a minute and look at the actual formula, because you have now gotten used to the standard t-test formula, which was just x bar minus mu sigma, the standard deviation divided by square root of n. And I just want to show you for a minute, it's not that much different. And this is not the formula. I'll show you the formula itself in a second, but I want to show you where it comes from. Because we are finding differences, there is no 1 x bar anymore. It's, sample 1 minus sample 2. In the same essence, there is no single mean anymore. There is a population mean from population 1 and a population mean from population 2. Now, remember what I said about the null hypothesis. mu1 equaling mu2. If we start with that assumption, this kind of disappears, doesn't it? Because we would have 0 minus 0. So ultimately, your formula for our pooled t-test starts to look like this without the mu1 minus mu2 because it's simply not needed. I also want to talk a second about the confidence interval. We're not going to do one in this particular video, and I will not ask you that on a test, but you will do some in math lab. Normally, we do a confidence interval for one population mean. We are taking our sample mean and developing an interval where our population mean would fall in. So if our sample mean was, say, 20, our interval might be, 18.5 out to 21.25. And we would say we're 95% sure that our population falls in there. But when we're comparing 2 populations, what we're looking for, the key word here, is the difference. Okay? So the difference is the difference between the 2 samples. So this final interval that you're going to get has nothing to do with the final population means of those populations. It has to do with the difference between them. So for example, if they're really, really close to each other, they're going to fall roughly around 0. So you could have like a negative 0.5 to positive 0.5. That would tell you that your population means are relatively close to one another because 0 falls within that interval. But if we did it where it was -1 to -3, notice there is no 0 in that interval. That tells us that it's very likely, since they're both negative, and we're starting with population 1, that population 1 is smaller than population 2. And vice versa. If they're both positive and there's no 0, then we would say that population 1 is definitely larger than population 2. But if it includes 0, you could say that the 2 populations, because there's a good chance of it including 0, are relatively the same. What I do want to focus on is the hypothesis test. All right, so here's your formula, and I'll show you your formula sheet real quick where you can find them on the formula sheet in Chapter 10. Please make sure you're reading this correctly. We've got all the information for the pooled test goes here. Here's everything for a pooled. We have the pooled sample standard deviation up here, formula for that. We've got the T-test statistic. If we can use pooled, again, we're assuming equal population standard deviations. That's how we find our degrees of freedom. And if we did have to do a confidence interval, we would use this as opposed to the test statistic, the hypothesis test problem. So there's everything for our pooled test that we're going to use right now. Again, you can assume simple random samples independent. You have to know they're independent. And you have to assume equal population standard deviations. You will not need to figure this out. It will be clearly given to you in the problem. When you're conducting your test, another thing you want to do, a little different from before, is define your two populations. All right? Tell me which one's one and which population you're going to call number two. They're either not equal, you get a two-tailed test. One is less than two, you've got a left-tailed test. And one is greater than two, and you have a right-tailed test. The steps are going to be very much the same. Here's your new test statistic, but keeping in mind we first have to find our SP before we can do our test statistic. And then just like with every other hypothesis test we've completed, you've got either your critical value approach or your p-value approach. Make sure you know how to do both, but I will only, on the final test, ask you for one. Step 5, of course, based on that approach you took. Sorry, there's a plane going over. Please make sure you draw your conclusion to reject or not reject. And then, of course, step 6, interpret. So what I want to do is you pull out your formula sheet, have that in front of you, and we're going to go ahead and work out a problem. So take a moment, read the problem. This is from our textbook. It's problem in Chapter 10, Section 10.2, number 10.48. I don't know the page, but you can find it. And it has to do with the data on household vehicle, miles of travel, VMT, vehicle miles of travel, are compiled annually by the Federal Highway Administration and published. If we took independent random samples of 15 Midwestern household and 14 Southern household, the question is to compare these and determine if at the 5% significance level, does there appear to be a difference in last year's VMT for Midwestern and Southern? So in other words, is there a difference between the annual amount that someone who lives in the Midwest drives compared to the annual amount that someone who lives in the South drives? That's what we're looking for. So let's get our hypothesis up first. I don't want to write in red. Our hypothesis, again, as I stated before, is simply mu1 equals mu2. I'm going to go ahead and call this Midwest 1 and the South 2. It does not matter which one you call 1 and which one you call 2, as long as you remain consistent through your problem. Now, for my alternative, we're looking for a difference. So that implies a two-tailed test, mu1 not equal to mu2. So let's get the information down. I'm going to jot down the information over here underneath the problem. It's given to us. We don't need to plug it into a calculator to get it. So the mean of population 1 is 16.23. The standard deviation is 4.06. The mean of population 2 is 17.69. The standard deviation is 4.42. Don't forget your size. The size of population 1, I believe, was 15. And the size of population 2 is 14. Other information, of course, we have our significance level is 0.05. Now, you want to take a look at your formula. That's this one right here. We have an x1, we have an x bar 2. We have our n's. What we need before we can even find our test statistic is our SP. You've got to find that pooled standard deviation. Remember I said they're kind of weighted, so the sample size of each is taken into consideration when this is calculated. So we have n1 minus 1 times s1 squared, and n2 minus 1 times s2 squared. So let's go ahead and calculate SP. So n1, so we have 15 minus 1 times 4.06 squared plus 14 minus 1 times 4.42 squared over, just double check, n1 plus n2 minus 2. 15 plus 14 minus 2. It's a pooled standard deviation. So your calculation has to fall between your two standard deviations. It's going to be between 4.06 and 4.42, slightly closer to the one that's weighted more. In this case, the 4.06, because it has slightly bigger sample size. So please take a moment. Make sure you are able to do those calculations in your calculator. Hit pause. You've got to practice the calculations and make sure you can get them right. I would do it in steps. Calculate each piece of the numerator first before you add them together. So you've got 14 times 4.06 squared. Make sure you're only squaring the 4.06. And then added it to 13 times 4.42 squared. And of course, divided by what it looks to be 27. And then at the end, take the square root. You should get, and we're going to take this out quite a few decimal places, 2372. The reason I'm taking it out as few is because when you have a number that you're going to use to calculate into another formula, it's best to have as many decimal places as you can, and usually taking it out 4 is a very good idea. If not, you have too much rounding error. So that's what I get for my SP. Now, for my test statistic. So for the test statistic, go back to your formula. Remember, x1 minus x2, SP on the outside, square root of 1 over n plus 1 over n sub 2. So we have 16.23 minus 17.69 over 4.2372, 1 over 15 plus 1 over 14. Again, take your time. Get what's under the square root first. Do 1 over 15 plus 1 over 14. Get an answer. Take the square root of that answer. Multiply it to get your denominator. And then subtract those two. And you should get, ultimately, negative 0.927. At this point, you can do either that critical value or that p-value approach. If we do the critical value or the p-value, either one, we need degrees of freedom. If you don't remember your degrees of freedom, it is given to you on your formula sheet, n1 plus n2 minus 2. And there goes my dogs, but I'm going to keep going. So it's 15 plus 14, which would give me 29 minus that 2. My degrees of freedom is 27. Now, you need a t-table. Remember, we are doing, again, let's draw a picture. This is a two-tailed test. Our significance level was 0.05. That 0.05, because it's two-tailed, needs to be split into 0.025 on either side. So what am I really looking for? I'm looking for a t-value of 0.025 at 27 degrees of freedom. So pull out your t-table, go to 27 degrees of freedom, let me pull it up, and here is my 0.205. So it appears to be 2.052. So negative 2.052 and positive 2.052. Clearly, there's 0. This is in the do not reject, sorry. It's in the do not reject region. The rejection regions are on the sides. These are your rejection regions. And this is going to be a do not reject. Same idea. If we were doing a p-value approach, it's a little bit different. Your p-value, your test statistic, the negative, move that up a little bit, the negative 0.927, and the opposite of that, because it is two-tailed, would go on, and you have to find this area. And clearly it's going to be a pretty big area because 0.92 and negative 0.92 are closer to 0 than what I drew. I did not draw anywhere near to scale. But to do that, you still go to 27 degrees of freedom on your table. This time, we don't need that middle column. And then you try to determine, okay, where is 0.9? Well, 0.9 is clearly way off in this direction. And when you look at your areas, as you move in this direction, your areas increase. So the last area we have is 0.10. So that means this side, which is half of P, because it's split in two, is greater than 0.10. But so is this side. And if half of P is greater than 0.10, then P is definitely greater than double that. You can multiply both sides by 2. Alpha was 0.05. Our conclusion, when we do a p-value, is P is greater than alpha. Same, we reach the same conclusion, do not reject. Okay? And what would our final statement look like? This is where you just need to come back here. And here's what you would write for your interpretation. At the 5% significance level, I'm going to get rid of the does, there does not appear to be a difference. So we are not rejecting, so there's not there. Does not appear to be a difference in last year's mean VMT. Or you can say there is not sufficient evidence. There does not appear to be a difference. So because we are doing a do not reject, you would state it in the negative that there does not appear to be a difference. And that's ultimately concluding that the means are relatively the same. That people who drive in the Midwest drive about the same per year as people who drive in the South. Now, I'm going to continue with this video, and I'm going to go over the non-pooled test. I'm not going to, and I'll tell you right now, we don't do a lot of these. In fact, you probably won't even see these on a test, on a cumulative test. But I do want to point out a few things. Again, don't worry about this part of the formula because that would be gone. In this case, we actually use the standard deviations. They are used within the problem itself. We do not find there is no S sub P. As I had stated before, the degrees of freedom formula is a little nuts. There's a lot more consideration that goes into how many degrees of freedom if we are not pooling those standard deviations. Again, I am not going to make you use this formula on a test, just so you're aware of that. Ultimately, everything else is pretty much the same. The only thing that changes is the formula a little bit. Notice under your assumptions, it does not say that you can assume equal standard deviations. So because we cannot assume equal population standard deviations, we cannot use the pooled test. We have to use the non-pooled test. The non-pooled test, if you look at your formula sheet, are located so again, there's that crazy degrees of freedom formula, but they're over here. Here's your non-pooled test. You've got the test statistic, and of course, if you need to find a standard deviation, that's going to be there as well. And it clearly says this is a non-pooled t-test. Your steps are exactly the same. You can review them, but everything is going to fall under the same category. I am going to actually jump to doing a review. Confidence interval is the same. Again, choosing between them, it's going to be quite simple. You're going to use, if you're reasonably sure that the populations have nearly equal standard deviations, you will be given this information. You use your pooled t-test. So here's a test that the assumptions for it says we cannot assume equal standard. There's nowhere where it says we can assume equal standard deviations. It has to do with stressed out bus drivers. The city of Stockholm felt that the bus drivers were stressed out, so they built a new bus route. And they kept certain drivers on the control route, which was the old route, and then they put some of the drivers onto this new bus route. And what they looked at is the bus driver's heart rate after completing the routes. So as I stated before you even do anything, you can just assume mu1 equals mu2. We're going to go ahead and call mu1 the intervention and mu2 the control group. So this is where it gets tricky, and this is why you have to define it. At the 5%, do the data provide sufficient evidence to conclude that the intervention reduces the mean heart rate? So if the intervention is group 1, and we want to see if it reduces it, we would have to say that mu1 is less than mu2. So here's a funny example. It's why I actually picked this problem of it, where an alternative hypothesis is kind of come up with before data is even collected, because you'll see in a second that even in the sample, mu1 is not less than mu2. So let's go ahead and jot down the information. We have X bar 1 was 67.9, S1 5.49, and N 1, 2, 3, 4, 5 looks to be 10. For group 2, X bar 2, 66.8, and you're given all this, you don't have to calculate it, 9.04, and N2, I was seeing if it actually gave it in the problem at all. What do we have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 times 5. So it looks like we have 31. Yeah, because they have that 80 out there. There is no S sub P. We don't need to do that, so we can jump right into our test statistic, which if you look at your formula, x1 minus x2, x bar 1 minus x bar 2, and then the standard deviation squared divided by n, standard deviation 2 divided by n sub 2, and the square root of that. So let's plug that in. And what you should do at this point is stop your video and attempt to calculate this on your own so that you can take the time to make sure you're getting it right. All right, I get, did you pause? Good, 4.59. I'm not going to do the degree of freedom formula with you. That delta, if I plug everything in, you can go ahead and try it on your own. If I go ahead and plug everything in, I will tell you I get 25.72, so please try that on your own. With degrees of freedom formula, to keep it robust, we can't go to 26. What you're going to do is always round down. So you're going to make that a 25. Let's do a quick critical value approach for this problem, which means we are going to do a left-tailed test at t of 0.05. Because it's left-tailed, everything's going to be there. We're going to look at 25 degrees of freedom. So go to the formula sheet, go to 25 degrees of freedom. 0.05 is 1.708 because it's a left-tailed test. We're actually going to use negative. And this is clearly, in fact, you don't even have to do anything here. The sheer fact you're doing a left-tailed test and you got a positive test statistic, as I said, this is an example of a hypothesis test that was set up without even knowing what the sample means were. Because how can you, with these sample means, really run a test that shows one is less than the other when the sample means aren't even less? So this is clearly a do not reject. And of course, our interpretation, at the 5% significance level, the data do not provide sufficient evidence to conclude that the intervention program reduces mean heart rate. Provide examples. So this is where you want to kind of expand it a little bit and think about why. So one of the things, and you can think of some things on your own, but one of the things you want to think about is, you know, you took a group of bus drivers that even though it was a stressful route, you just put them on a brand new bus route. That may actually cause their anxiety to go up initially. So that's something to think about why. And did they control for all the other factors? Age, weight, general health, and condition. So this ends this particular video. Our next one will look at those dependent paired samples.